All right. Okay. Happy New Year, everyone. Okay. So today we will come to the last part of the course. Okay, which is about the compensator design using frequency response technique. Okay. Before we move on, okay, just a quick reminders. Okay, I guess you may start probably to able to access the PK07. Okay, so you access that one. Okay, to provide any feedback if there is. Okay, and then also did you check the final exam schedule? Okay, so if I recall correctly, it should be on 7th February, okay, which is Monday for the control class, right? Control courses. Okay, so this would be a face-to-face final exam, right? Unless there is some special things happen, right? So for now, it would be a face-to-face final exam, right? So just prepare as you have tried for your test too, okay? So bring your stationaries and other things, okay? And then for this finals, probably there is one last particular questions that asks you to maybe do some design, okay? A quick design, okay? So that design questions may not specify any methods, okay? Meaning to say you may want to use root lockers or you may want to use the plot, right? Not mentioned, right? But in the question paper, I already provide the semi-log, empty semi-log for you, okay, if you would like to use it, right? But other than that, okay, it's free to use root lockers technique as well, okay, whichever convenient for you, all right? That would be on the one last questions in the final is, as I recall, right, there is one questions for simple design only, okay? So you may use any methods you like, okay? And probably, I'm not sure whether the BPS site may provide the graph paper, okay? If no graph paper, then you just use the answer book lah, okay? You draw the axis there and plot your things lah, okay, using ruler. So make sure you bring your ruler lah, okay, to draw the scales and so on, right? So that would be how you can sketch your root lockers, okay, without the graph paper, right? Then on the quiz and the assignment, all right? So quiz, I will start to post the quiz online next week, okay, as a revisions, okay? So this quiz probably may takes you 10 or 20 minutes to answer, okay? Just objective question, right? Online, just click whether it's true or not, the statement and so on, right? So simple quiz, okay, just to refresh your understanding. So you just open book, right? Time is up to you and just submit before the due dates of the quiz, that's all right? Then on the assignments, if you recall back there, we have already gone through the initial stage. You already have the transfer functions and so on, right? Okay, so what you may need to do now is, I guess the last task I passed to you is to plot the root lockers, okay? So now your last task before you submit your assignment is to adjust the, or to propose a controller design, okay, for your transfer function, okay? You just simulate it using Scilab or MATLAB, okay? Just simulate, okay, by putting your own design criteria, okay? You think whether it's up to you, okay? You just set your own target, okay? How fast you want the motor to turn, okay, to achieve certain characteristic, or how accurate the motor should position itself, okay? So that would be your design criteria. Then you adjust your your controller, okay, accordingly, and simulate, and then your assignment is complete. All right, so just finish up that final part of the controller design, then you can start to compile in the PDF and submit. I will provide the assignment submissions link, yeah, link, or yeah, in the Google Classroom, right? So that would be the last assignments part. Okay, so the due date for this assignment would be before your final, right? Before your final, but just whenever you're free, you just do it, right? So that's why I start early, okay, so that you can do a little bit, okay. So now you just finalize, okay, apply what you have learned throughout these few chapters, okay, set your on target, apply it, okay, that's all, right? So any questions on this? If no, then we
Good morning,
will,
Doctor.
yeah,
Can you hear me?
yes.
Recently, I saw a news about the KPM will there will be an additional holiday for the Chinese New Year. Will that affect the exam final timetable?
Uh, so far, no news
There's no any
from,
news from UMS, right?
no news from your miss side. So
Okay.
probably, how long is it? Until when?
Not
The,
sure. I think until 3, the holiday 3rd of February.
okay, I guess the final exam uh, would still the same. Okay, only those date affected they may shift it lah, probably.
Okay. Thank you, Doctor.
Okay, okay. So on today's topic, we will use the frequency response technique to design our compensator, right? And we try to figure out what is the relationship between all those so-called important control parameters, okay, or desirable parameters, especially on the damping ratio, okay, and how we can use the frequency response, okay, uh, results, okay, on the gain margin and also the phase margin, okay, the gain margin, right, and the phase margin, and how they are related to all those um, characteristics, okay. For example, for the unstables, okay, conditions, you may know when it will start to become unstable, right? And at the same time, all this phase margin and the gain margin may provide you with certain uh, informations about the damping ratio, okay, or the damping ratio also related to the percent overshoot probably, right? So from there you may start to able to adjust according to your needs, right? So most of the design of a control systems, okay, as you start to notice all those questions, they may give you a criteria, right? So all those design must start with a criteria, okay, and those criterias probably uh, somehow they are translated in the form of maybe settling time, okay, peak time, right, or maybe percent overshoots, okay, and so on, right? So all these items again, they are somehow related to maybe damping ratio, okay, or the natural frequency omega n, okay. So when you can start to see, okay, from the design requirement, okay, now you translate into the control parameters, okay, the damping ratio, the natural frequency, okay. Once you can flow from the design requirement to these two parameters, okay, then now using these two parameters, you can start to figure out what is the P or PI or PD, okay, that you should adjust, okay, to achieve this desirable omega n or damping ratio, okay. So this is the design process lah, right? So although from the early stage, okay, we learn about time response, okay, figure out what is the the take time, setting time, okay, and then we slowly evolve into the stability, the relationship between the time response and these two parameters, okay, and now the design is how we can adjust, okay, so that we can meet this or achieve this damping ratio and omega n, right? So the easiest way to control the transient response would be to adjust the gain, okay, the P itself, right? As you know, when you increase the K value, okay, the P, okay, then the response will become faster, right? Okay, so that is how you can adjust it, right? So same thing now, we try to use the similar approach, okay? Find out what is the relationship between the phase margin and the damping ratio, okay? For this so-called frequency response technique, okay? Here is the relationship, okay? We could see that the phase margin, okay, the PM are related with the damping ratio by these particular equations, okay? These particular equations, okay? So the phase margin is equals to arctangent of 2 damping ratio divided by square root of minus 2 damping ratio square plus square root of 1 plus 4 damping ratio 4, power 4, okay? So meaning to say, if from your design requirement, okay, and then from that particular design requirement, you can translate into the desirable damping ratio, okay, then you can get the phase margin that you would like to have, okay, to be adjusted, okay. And this phase margin can be, since these equations are a bit difficult, okay, we can approximate uh, yeah, we can approximate such that the damping ratio is about the phase margin divided by 100, okay. This would be a good approximation when the phase margin is less than 70 degree, okay. So this is one of the approximations that we can use, okay, to help us to do the design, right? So the design procedure, as we can adjust the gain, okay, very straightforward, okay. Once you can plot the Bott diagram, okay, from the Bott diagram we can find out what is the phase margin, okay, sorry, the phase margin and the gain margin, right? So this phase margin, if we know that 180 degrees minus, okay, is the stability line, okay. So if we increase up to this particular point, okay, the phase margin point, okay, therefore this would become 0, right? Okay, so this would be the required gain that we have to increase, okay, if it is in the negative side, okay. If it is on the positive side, then you can decrease it, okay, accordingly, okay. So here is once you can identify your phase margin, okay, from the damping ratio or maybe the percent overshoots, probably, right? Then therefore you can find out what is your uh, frequency required, okay. So here is your you can see that you have a frequency line as well, okay. So you can find out what is the frequency, and at the same time you know what is the required gain to be adjusted, okay. So you can have this so-called adjustment, okay, that you can make, okay, to design or to increase the P, okay, the K value itself, right? So let's take an examples for this, okay. So here is a simple design questions that require you to find out the value of the K, okay. That would give a 9.5% overshoot, okay, in the transient response when we put in a step input, okay. So basically, if you have many blocks, at the end we still combine it as one lah, okay. So, and most of our questions also we only deal with the unity feedback loop, right, for simplicity lah, right? Okay, so now the step would be, first we have to plot the plot diagram. Okay, so we just plot it, okay, accordingly. But when you have a k value, an unknown k value, okay, you can just put any value that you like. Okay, and here we just choose a 3.6. Okay, you can somehow normalize it lah, okay, accordingly. All right, without the k, all right, or any values that you prefer, right? So here we choose 3.6, and it will start with 0 dB at omega 0.1. Okay, so this would be the original line. All right, but this is just a k value that we assume. All right, so not necessarily the correct one. Okay, so what we would do from this is that we have to figure out what is the corresponding damping ratio, okay, from the overshoot lah. Okay, so the design require us to find out approximately 9.5% overshoot, and if we use this formula, this relationship, okay, for a second order, yeah, probably a second order equations, okay, so we could approximate, okay, the damping ratio as 0.6, okay, using these equations. So once we approximate that one, then we use back the equation that we have previously. Okay, if you want it to be accurate, you can use this. Okay, if you don't want it to be accurate, you can use this. All right, so it's up to you lah. All right, so you can see that we get 59.2, the much accurate one. Okay, so if it is not accurate ones, okay, you can see that damping ratio is 0.6. Okay, so damping ratio is 0.6 multiplied by 100, you get 60. So the phase margin that you will use is 60. Okay, the accurate one will give you 59.2. Right, so that is how you can see, yeah, it's quite close. Okay, the approximations, right? So whichever you use is okay, as long as you put in your equations, okay, in your test or exam lah, okay, or even in during your work, okay, you have to write down. Okay, as we work as an engineers, all these facts or equations must be properly documented, okay, because it would be a reference for others engineers to check, right? What is our assumptions or equations used to obtain all this value, right? So here we use the accurate equations, we get 59.2. Okay, so from the 59.2, what we would do is that from the minus 180 degree, we have this margin, okay, this phase margin to be adjusted. Okay, so 180 minus 59.2 will give us 120.8 approximately, or 120 lah, okay, if we use 60 degree. Okay, meaning to say we would adjust from 180 degree line in the phase to 120. Okay, so it intersect at this particular point, okay, at this particular frequency. Right, so what it means is that at this particular point we would like to adjust this this line, okay, or this point to a 0 dB. Okay, so this is the magnitude that we would want to adjust, okay, so that we can achieve an approximate of 9.5% overshoot. Okay, so this occurs at a frequency of approximately 15, probably. Okay, the accurate one would be 14.8. Okay, so it's approximately 15, 10, 15, this is 20. Okay, so approximately 15 there. Okay, so what we can see that is when we do a cross line over here. Okay, so we can see that this magnitude, okay, at 14 frequency, 14.8 radian per second. It's approximately 44.2 dB. Okay, 44.2 dB. Okay, it's meaning to say we have to increase 44.2 so that this point become 0 dB, right? Okay, so from this ideas, or from this, sorry, changing, where is, okay, from this information, okay, we can now start to find out what is the proper K, right? How we can adjust 44.2 dB is that originally the K is 3.6, okay, our new initial assumptions, okay, to plot this line. Okay, so what we would do is we calculate the corresponding gain, okay, for the 44.2, okay, using this equation, 10 to the power of 44.2 divided by 20, okay, because we know dB, this one, okay, the log, okay, we will give us 162.2, okay, this is from this magnitude equations, okay. This is our unknown, right? So our unknown is this one. So eventually, when we do this one, we get 162.2, okay? So this would be the gain that we would need to put in to get 44.2 dB, all right? So once we get this 162.2, we multiply by the initial K, okay, we get 583.4, okay? So this would be the gain, okay, that would shift this particular point to this new line, right? So this is how we can estimate the K value, okay, or to design the K value, right? So once we get this K value, meaning to say we are almost there, okay? So normally in design, we just cross-check again, okay? So in the final assignment, okay, in the assignment as well, okay, after you do your design, okay, you get your K value or maybe the PI value, PD value, okay, you just simulate again, okay, using that particular value to check whether you have obtained the desirable value or not, right? So this is just to double check. So by putting this 583.4 into the equations, into our simulators, okay, then it would give us approximately 9.48% overshoot. So it would be very close to our target. Therefore, we can now confirm that the value should be 583.9 multiplied by 100, okay, divided by the initial transfer function, okay, because we have 100 over here, right? So multiply by 100. Okay, so this is the adjusted open loop transfer function. Okay, so again, just be aware of the terms being used here. Okay, open loop transfer functions over here, okay, even though this is closed loop, okay, referring to this multiplication, right? Okay, multiply by the feedback, okay, which is 1. Okay, so this multiply by this, multiply by this, multiply by this, okay, and we would term that as the open loop transfer functions, right? So in the final exams or maybe in the test on that day, okay, sometimes you may see that I wrote in the question, they write there, the given open loop transfer function is this, okay? It means it doesn't necessarily means it is open loop, but it means you have a transfer function here with a unity feedback, okay? So that is the how you can interpret the questions, right? Next would be on the steady state response characteristic, okay? So how we can adjust this would be on the relationship between the steady state error and the plot itself, okay? So we would obtain the result from the unscaled maybe or non-normalized dot plot. Okay, so we just plot accordingly, no need to normalize anything. Okay, so the position constant, the kp itself, okay, from the relationship we found that the gs equals to k with a product of all these summations of products of zeros divided by products of the pools. Okay, so since this is a type 0, initially it should be a flat line, a constant, okay, where we would found that this kp, since s when it is approaching 0, okay, this would be 0, right? So it become only 0 and pools. Okay, so this would be our relationship. So the kp would be equals to the k product of zi divided by product of pi. Okay, and this is the value of the low frequency axis. Okay, you can see that the value of the kp is here. Okay, meaning to say when you plot the dot plot, okay, without any normalizations, okay, this particular value actually is the value of your kp. Okay, that is the value of the kp itself. Right, for a type 1 system, again, when you plot it out, okay, we notice that before that, okay, we have to realize that the slope will actually in the decrease slope, okay, because of the type 1 characteristic, the s over here, okay, which with a 20 dB per decade. Okay, therefore when we plot itself, we would expect something like this. Okay, if it is a type 0, we would expect something like this. So from the dot plot itself, we can already see the system type. Okay, the system type is 0 if you start with a flat line. Type 1, it will start with minus 20, okay, at low frequency. Type 2, it will start with minus 40. All right, so that is one of the characteristics that we can see lah. Okay, then how we can extract the relationship or information with the steady state error or the constant itself would be, for the type 1, we have this kv equals to k, again the same equations. Okay, and this is basically the x-intercept or the frequency axis intercept. Okay, so when we dot extend this line, okay, we will see this value actually is the kv value. All right, so this is the kv value, right? And the initial values would be this value. Okay, same thing for the type 2 equations. Minus 40 slope, okay, when we plot and we found out this is minus 40 dB slope, then we know that the system type is type 2. Okay, and the relationship with the ka is the square root ka. Okay, square root ka over here. Okay, this a should be the this type of a. All right, so the intercept is the square root ka. Okay, so you'll be able to find out what is the ka, okay, from the dot plot. All right, so once we see the relationship of the gain and also with the so-called a little bit informations about the error, okay, now when we come to the compensator, okay, our compensators, when we design, we have two purpose only, right, so far. Okay, one is to control the transient response, and the second one is to improve the steady state error, right? So in order to improve the steady state error, we can somehow increase the system type. Yeah, increase the system type, then it become better and better, right? Okay, so that is the design technique or strategy lah. Okay, we increase the system type. Okay, then the steady state error will improve. Okay, for the transient response, if we increase the gain, okay, and when we increase the so-called differential terms lah, okay, then the system will respond better as well. Okay, so this is what we intend to do in the compensator design, right? So for a bot plot itself, what we would do is we will employ some so-called parallel design process. Okay, because we already have a bot plot which tells us the gain as well as the phase, right? Okay, so what we can do is that from that we adjust directly, okay, both directly over there. Okay, we don't need to like adjust the gain first, then the other one accordingly lah. Meaning to say in that way, right? So for the lag compensations, okay, lag compensations is the first one, okay, the PI, okay. For the lag compensations, what we would intend to do is to increase the so-called system type, right? Okay. So what this lag compensator will do is that this is the red line is our design. Okay. So typical lag compensators characteristic would be in this way. Okay, so you just have to remember this pattern. Okay, for the gain and for the phase is in this pattern. Okay, so when we see this pattern, this is the pattern for the lag compensator. Okay, then when we see the other pattern, okay, reverse pattern, okay, then that would be the lead compensator. Okay, so just have to, for now, just have to remember the pattern first. Okay, lag compensator going down. Okay, lead compensator, this one going up. Okay, so that is the reverse way of it lah. Okay, so what we would do is that, remember when we plot the frequency response or the butt plot, okay, we can always add up and add up at the frequency point, right? Okay, meaning to say if you know this pattern, okay, you can also add them up. Okay, so this original, the lighter blue is the original uncompensated system. Okay, and this is the lag compensator that we intend to incorporate into our design. Okay, so eventually when we total them up, okay, so this one no dB to be total up, so it will follow up accordingly. Okay, but then this one it will decrease, right? So if you use the table, okay, you will found out that this point will decrease to this point. Okay, so you draw a straight line, okay, and so on. So this is how you would see that the compensated line or the system will change, okay, due to the implementation of the lag compensator. Okay, so this is the effect of our lag compensator. Okay, same thing for the phase plot, right? So the lighter blue, okay, which is a straight line all the way, okay, now change, okay, when we implement this one. Okay, so because of this, it will go down and then go up again. Okay, so this is the pattern of the lag compensator, right? And from this so-called lag compensator, okay, what it does is that it improves the static error constant, okay, as well as it increase increase or improve the transient response. Okay, that's why we would say somehow it is a parallel design. Okay, how we do this is that for the static error constant, okay, we increase only the low frequency gain. Okay, we increase only the low frequency gain. Okay, so this is what we do lah. Okay, we only increase the low frequency gain. Okay, the rest we reduce it. Okay, then for the transient response, we would increase the phase margin. Okay, we increase the phase margin. So we can do the design criteria. Okay, we can meet the design criteria by adjusting these two particular things, right? And that would be reflected by the lag compensator patterns over here, right? So once we do that, okay, we can able to, let me shift the Google Meet bar over here first. Okay. Okay. So here we can see that the low frequency gain for the system can be made high, okay, to give us a good KV value. Okay, this is the KV value. Okay, without creating instability, right? So this is the non-compensated line. Okay, the KV is over here. Okay, then once we adjust it, okay, reshape, then therefore it change as well accordingly, right? So this one shift up, shift down a little bit, okay, to the desired phase, okay, nearer to the 180 degree, right? So the design procedures more or less similar for both lag and lead. Okay, first again we set any gain k value that we want, okay, that satisfy the steady state error. Okay, we plot it out, then we start to find the frequency where the phase margin is 5 to 12. Okay, this is just a general rules. Okay, you can put 5, 10. Okay, for the phase margin. Okay, then we start to select the lag compensator. Okay, so this is where initially I told you to remember the pattern. Okay, so this is the idea lah. Okay, you have to remember the pattern. Okay, and then you select the corresponding compensator patterns, okay, to be inserted. Okay, so once you insert, then you will start to fill in all the parameters accordingly and see whether the system can compensate or not. Okay, so that is the ideas, right? So here we relies on this particular settings. Okay, remember this one, 5 to 12 degree, okay, and the lag compensator patterns. Okay, so the initial gain to meet the steady state requirements should be adjusted at the beginning. Okay, then the lag compensators is about minus 20 degree. Okay, this is the characteristic of the lag compensator. Okay, minus 20 degree, right? Meet the transient response, okay, by setting the 0 dB crossing the magnitude plot, right? So here, if we have these transfer functions of the lag compensator, how it would looks like is that when we put in all these values, okay, we can see that the Kc, this value, the Kc value, the lag compensator gain value, Kc is equals to the K divided by the attenuation factor alpha. Okay, so this would be the values lah, right? So you just recognize when we rearrange, okay, this would be attenuation factors, okay, and the Kc value can be comprised of the K divided by the alpha. All right. So now you can try to follow this. Okay. The idea is very similar. Okay. So if we have this particular transfer functions, okay, s plus 1 over 10 divided by s plus 1 over 10 multiplied by 10, okay. So what we do, we plot it out, okay. Then we start to assign and approximate values of PM, okay, to our lag compensator and adjust it, right? So that is the readings part, okay. You can read it, okay. So we just go through an examples, okay, directly, okay. Same problem, okay, same problem just now, okay. But what we need to achieve here is to yield a 10 times improvement in the steady state error, okay, over the the previous system. Okay, so our previous system that we have designed, we get about 580 something, right? The K value we get is 580 something. Okay, that would give us a 9.5% overshoot. Okay, so what we would do now is we want to maintain this one, but improve the steady state error. Okay, improve the steady state error. So same diagram. So what we would do now is that I think this one is slide number 7. Later you check back again, all right? Because I add in slide at the beginning. Okay. Now, so the previous one we get 583.9. Okay, give us 9.48%. Okay. So from that one, we get the KV is 16.22. Okay, let's check if it is true or not. Yeah, cannot see. Okay, never mind. Later you can try it. Okay, to replot it lah. Okay. So you will get the KV approximately 16.22. Okay. Then from that 16.22, we want to improve 10 times. Okay. 10 times. So what you would do is that you would multiply by 10. Okay. Now it becomes 162.2. Okay. And 162.2, the K value now would also multiply by 10, right? Okay, 10 times. So 5839. Okay, so this would be our open loop transfer functions. Okay, and the dot plot value would be 5,839. Okay, so what we do now, we try to put it in. Okay, so we try to put it in. Okay, remember the pattern of the lag compensator. Okay, that we intend to put into our design now. Okay, so the phase margin required remain the same. Okay, because we do not adjust this one. Okay, in our design guideline, okay, we would increase the phase margin by 5 to 12%, right? So now we just choose any number that we like. Okay, for simplicity, we choose 10 degree. Okay, so 59 now increased to 69. Okay, so if this is 69, then it should be about 110. Okay, minus 110. Okay, and we do the same thing lah. Okay, so we do the same thing. Check what is the frequency, corresponding frequency. Okay, And also we check what is the magnitude. Okay, so the corresponding frequency is 9.8. The magnitude is about 24, right? From the diagram itself, okay, about 24. Now, this is what we have now, okay, the uncompensated one, all right? So the frequency from that particular frequency, okay, 24, and the frequency of 9.82, what we have to do is we adjust the so-called the attenuations. Attenuations means something like reductions, okay, something like reductions. So what we would do is using this 24, we want to minus it, okay, so we would minus 24 because it is a plus 24 over here, okay, plus 24 dB, so we would provide a minus 24 dB at 9.8 radian per second frequency, okay. So we would write in the way of attenuations of minus 24 dB, okay, reduce 24 dB, right? So what we would see now, okay, is that the lag compensator equations would be given as such, okay, and the attenuations frequency is 9.8, right? Okay, 9.8. Okay, 9.8 is somewhere here. Okay, so what we would do now is to draw the compensator pattern. Okay, remember, straight, slope, straight, right? Okay, straight, slope, straight for the lag compensator. Okay, so what we would do now is that we select a higher break frequency, okay, 1 decade before lah, okay, so 9.8, we choose 0.98, okay, so we take this point and start to draw a minus 20 dB line over here, okay, so minus 20 dB line over here and then go straight. So eventually this line will reach 0.062 radian per second, okay, when we draw a 20 dB line over here, okay, so until it reaches 0 degree, right? Okay, and this line is minus 24. Remember, we would like to remove that 24 dB, right? So this 24, we draw a straight line at minus 24 that we intend to reduce, okay? Draw a minus 20 dB per decade line, okay, until it reaches 0, and then draw this one, okay. So this is our design lag compensator, okay. Now once you have this one, you just combine them together with the original, okay, then you have the compensated system line, okay. And the K value we already set is 5839, okay, and the lower frequency is now to be about 0.062, okay. Therefore, our transfer functions now for this one would be 0.063, okay. How you get this one? Okay, you just use this formula lah, okay. 0.062 divided by 0.98, okay, 0.98, our attenuations frequency over there, okay. So you get 0.063, okay. This would be our value to be inserted over here, bracket s plus 1 over t, okay, which is 0.98, okay, divided by s plus, again, this one is the low frequency, okay, this one is the low frequency one, okay, so which is 0.062, okay. So if you get this one over alpha t is 0.062, you can rearrange, okay, you would get all the other values, okay. okay, including this one. Okay, right? Okay, so once you get those things, you're already able to identify all these lag compensators parameter. Okay, so this is the lower frequency 1 over alpha t. Okay, and from that you would get 1 over t, as well as you can get other things. All right, so from that you can recheck again. Okay, put them into simulators, okay, and simulate whether it is correct or not. Okay, if it is more or less what you are desired, okay, then yeah, that's good to go, right? If not, then adjust again. Okay, continue to adjust, right? So that is how we approximate. Okay, recall back what our try and error values. Okay, we try to increase by 10% over here. Okay, that is our design changes. Okay, that influence all these changes over here, right? And for the lead compensator, very similar technique. Okay, very similar technique. Okay, so what we would result into is that the if you increase the phase margin and increase the phase margin frequency, that's all. Okay, so what we do here is we try to shift this forward. Okay, shift this forward, okay, by increasing the phase margin. Okay, increase, okay, instead of attenuate them just now. Okay, so this is the pattern that you have to remember. Okay, this pattern, okay, and this so-called combine after we combine. Okay, so the equations is in this way. Okay, just now we have the kc, right? Okay, that kc is forgot, over k over alpha, I guess, right? So here you have one over beta over here. Okay, and the other equations are more or less similar. Okay, so here we have this particular curve. Okay, that's to help us to adjust properly, okay, according to all those omega t. Okay, the peak of the varies will change according to the beta value lah. Okay, so for the designs for this little bit more complicated. Okay, little bit more complicated, but nevertheless very similar. Okay, you have to remember is the relationship. Okay, so here is the relationships between those parameter. Okay, the phase angle of the lead compensator, okay, with the omega and the uh, phase. Okay, so here we have three particular equations that we may use later on. Okay, related to the compensator magnitudes. Okay, right, so we just go into the design now. Okay, very similar. Okay, but maybe a bit longer lah, right? Closed loop bandwidth. Okay, plot the both magnitude and phase diagram. Okay, find the phase margin. Okay, then do the necessary adjustment to our phase margin. Okay, okay, by inserting the lead compensator, the patterns that we would like. Okay, so here is examples. Okay, we directly go into examples. Okay, to design the lead compensator, what we need to do is same equations. Okay, same system, right? So this system, as you can see, very similar to your assignment as well, right? You are dealing with motors. Okay, so what you can do is you have to know the design requirement. Okay, it can be 20% overshoot. Okay, with a desirable steady state error kV equals to 40. Also required a peak time of 0.1. Okay, So that those things may somehow related to this, okay? And we have to find a way to relate them, right? As I mentioned earlier in this lecture, okay? So we try to relate all those things, okay? How we can relate them is that we have this bandwidth frequency, okay? Bandwidth frequency, okay? So the closed loop bandwidth needed to meet the speed requirement of peak time 0.1 second is given by this so-called formula, okay, or relationship, okay? The TP is 0.1, okay? The frequency is about 0.456, okay? Because of 20% overshoot, okay? 20% overshoot, okay? So remember this formula, okay? Then the bandwidth would be 46.6, okay? This one put in into your equations, okay? So you roughly get the bandwidth uh, frequency, okay? Then to meet the kV value, which is 40, so we must set the previous one, okay, to 144,000, okay, 40 times lah, so called, right? So we just adjust this accordingly. This is based on the final value theorem, right? So you get this one, okay? Now what we would do is that from the uncompensated 1440 originally, the phase margin is 39, okay? Okay, to find the phase margin, you just have to check when this is 0, what is the difference in phase, right? Okay, so the phase margin is 34 at the frequency of 39.6. Okay, this is about 30 radian per second. Okay, so what we need to do is we have to figure out what is the additional phase margin to be increased. Okay, so we would see that it needs to be increased to 48.1, okay, because of the overshoot percent, okay, 48.1, okay, overshoot percent over here, okay, the damping ratios, okay, then adjusted over there, then you will see that it is equivalent to 48.1, okay. Therefore our target is 48.1, not 34, okay. So what we need to do is we need to do some correction lah, okay. And since this is about 10 degree probably, okay, so we assume the 10% corrections factor, okay. So 48 minus the original, okay, then add back a corrections of 10%, so we get roughly 24.1, okay. So 24.1 is our phi maximum, okay, that you see these equations in the previous boxes over here, okay? Phi maximum, okay, that relate to the beta, right? Okay, so once you get this phi maximum 24.1, you use that particular equations to calculate the beta, okay. So eventually you get the beta is about 0.42, okay. So once you get the beta, then you can calculate this GC as well, okay. So using the 0.42 lah, okay, insert into it, you would get the relevance GC values, okay. So now it would give you approximately minus 3.76 over here, okay. So from that particular informations, you would see that your systems now would have a new phase margin frequency of 39. Okay, previously 29.6. Okay, now it's 39. Okay, 29, okay, to 39. Okay, somewhere here. Okay, so from that particular values, we adjust again, use another relationships. Okay, the boxes. Okay, remember the three equations, them in, you would get all the parameters 1 over t or 1 over beta t. Okay, so eventually you get these two parameters, you can put into your compensators transfer functions. Okay, and this is your desirable values. Okay, so once you get this one, test again, right? Put into your simulators, okay, and check whether it is correct or not. Okay, so that is how you can do that. Okay, so guess this one I will not go into detail. Okay, I will not cover this one. Okay, so this one you just have to get exposed, that's all. Okay, there you may also design for a lead, like lead. Okay, like lead means your PID design. Okay, something like this. Okay, the design may take more more times. Okay, but very similar. Okay, very similar. You just do one leg. Okay, then the lead. Okay, according to where you want. Okay, and also this one, Nyquist Criterion, I will not cover it as well. Okay, just an exposures that when we come to control, we would also see this term Nyquist criterion. Okay, and this Nyquist criterion is one of uh, uh, popular design technique as well. Okay, for compensators. Okay, so but nevertheless we have covered enough already. Okay, using the root locus as well as the bot plot. Okay, these two is sufficient for the basic understanding. Okay, Nyquist is again a type of frequency response technique. Okay, another type of frequency response technique that you would able to plot in this form. Okay, something like this. Okay, so we call this as a Nyquist plot. Okay, and then we can transform and find what is the relevance. Again, all those parameters lah. Okay, in terms of frequency response and so on. Okay, that we would not cover. Okay, in this course, right? Just an exposures for you that they are other techniques. Okay, and Nyquist is one of them, right? For the design, right? So any questions before we end this topics, and this would be the last topic to be covered in this course, right? Any questions?
Doctor,
Yeah.
you hear me?
Yes.
So the purpose of those root locus and body port magnitude is to find to make the system more stable, right? To start at 0.
Yes. Yes. One first is to make, for sure we want to make the system more stable. The second thing is we want to improve the performance. Okay, because as you can see, the when we do the compensator, we always try to improve the steady state error. Okay, to reduce the steady state error if there is lah. Okay, and then also we may want it to respond faster. Okay, to reduce the settling time and the peak time.
Okay, thank you, Doctor.
Okay, so that would be our main purpose lah in the design. Okay, if everything is fine, then you don't have to do this PID lah. All right. So this PID concept are quite common as we can see. There is the temperature control unit, right, that I have shown in the pictures in the last, I think, last two lectures, right? Okay, where you can put in the P, I, and D value. Okay, and those values are actually from all these simulations. Okay, once you are satisfied, then you can adjust it. Okay, so that the temperature sensors will respond accordingly. Okay, why there is a temperature control unit in this way is that when we mix maybe uh, a water tank, okay, a water tank where we want to control the temperature of the water. Okay, so if we increase the heaters, okay, the water take times to heat up. Okay, and once you heat it too fast, okay, then it takes time to cool down. Okay, therefore this PID controller come into play lah. Okay, you have to model the system, okay, accordingly and adjust so that the heater, it can heat up very fast, and then before it reach certain time it will slow down so that it will not overheat. Okay, so that is the purpose of this PID and so on. For your assignment is up to you. Okay, you may include PID or not, depends on your target, so-called target design. Okay, you may set your target to improve both transient response as well as the steady state error if there is. Okay, then in that case you may need to use PID. Okay, if no, then you may use PI or PD. Okay, depends on what you need. Okay, so that assignment is just to expose you on how you can relate, okay, from a system, okay, until the design part only, right? So any more questions? If no, then probably tomorrow we will not have any class or tutorial. Okay, I will prepare for your quiz as well as maybe I will communicate with those who haven't taken the test too first. Okay, when they can take it next week. Okay, then next week we may arrange short maybe tutorial questions sessions. Okay, maybe I just run through some discussions on questions or maybe on the assignment as well next week. Okay, since we have the maybe 2 more weeks, right, to go before the holidays and so on. Okay, so these few weeks would be a revision weeks for you. All right, so if no, then we will end these sessions today and we will meet again next week. All right.
Okay, thank you, Doctor.
All right, see you. Bye bye, stay safe.